It's really kind of incredible when you think about just how far AI has come,
Hmm.
like these large language models. They can actually generate text that sounds almost, well, human.
It's pretty amazing.
Yeah, and have conversations that are coherent and even make decisions on their own in certain situations. And, when you really think about what makes all of that possible, there's this one key factor.
Memory.
Yeah, memory,
And it
exactly.
often gets overlooked.
Yeah, it really is kind of the foundation that allows these systems to really grasp context, hold on to knowledge, and really truly learn, over time.
Right. Without that ability to remember and recall information, even the most advanced AI would be stuck in the present, kind of processing each new piece of data as if it's seeing it for the first time.
Like it has no history.
Right. Exactly. Memory is what gives them the ability to kind of build on those past interactions and really understand that bigger picture.
And that brings us to what I've been like totally geeking out on lately, and that is how LLMs and AI agents are really kind of revolutionizing their memory capabilities.
Yeah. It's a really exciting area.
I've got a whole stack of research here, like detailed analyses of all these cutting-edge LLM architectures and deep dives into the latest memory technology advancements.
So much going on.
Yeah, our mission today is to break it all down, uh, extract like the most important insights into how these systems are moving beyond the memory limitations that we used to see in the more traditional designs.
Right. How they're evolving.
Exactly. Think of this as your your shortcut to grasping this incredibly dynamic field. It's moving so fast.
And it's important to remember, or should I say, to recognize that memory in AI. It's not just the single.
It's not like one size fits all.
No, not at all. It's actually a whole landscape of different architectural approaches, and the underlying technology is constantly evolving.
It's a complex system.
It really is.
Okay, so let's start with the foundation. The basis for a lot of these advanced LLMs, and that's the transformer architecture.
Yep.
Now, for anyone who's maybe not super familiar with this at its core, a transformer uses these mechanisms,
Hmm.
things like self-attention and multi-hit attention.
Right.
So can you kind of break down for us how these models actually uh, decipher the relationships between words, within text?
Sure. Imagine you're reading a sentence and trying to really grasp the meaning.
Sure.
You don't just process each word in isolation. You intuitively understand how each word connects to the others, right? To form a coherent thought.
We do that naturally.
Right. And self-attention basically allows the model to do the same thing.
Okay.
So when it's processing a particular word, it looks at all the other words in that input sequence and figures out, how important each one is to that current word.
It makes those connections.
Yeah, exactly. And multi-head attention kind of takes this a step further.
Okay.
It does this calculation multiple times in parallel, so the model can capture like a richer set of relationships, considering things like grammar and meaning and all those nuances.
Oh, wow. So doing a lot at once.
Right, simultaneously. And that's basically how transformers understand the context of a piece of text.
So it's like it's always assessing those relationships between the words.
Exactly.
Okay. But as amazing as all of that is, these transformer architectures, they do have their limitations, their memory constraints.
They do.
And we're talking about challenges with those really long sequences, right, and fixed input sizes, and the fact that they don't really store information from one interaction to the next.
Yeah, those are the big ones.
Okay, so could you go into a little more detail about each of those for us?
Sure. So one of the biggest bottlenecks is that the computational cost of the self-attention mechanism scales quadratically.
Quadratically.
Yeah. So for an input sequence with a length of n, the computational cost is roughly n-scored.
Okay.
Meaning as the text gets longer, the resources needed just explode, making it really difficult to process long documents or conversations.
It just gets too big too fast.
Right. And then there's the fixed size input window.
Right.
Models are typically trained with a maximum sequence length, and if you feed them something longer, it gets cut off,
Cool.
losing potentially crucial information, especially from the beginning.
So it's like it's got a hard limit.
Right. And as you mentioned, standard transformers are basically stateless, so they don't have a built-in way to preserve memory from one sequence to the next.
So each interaction is like a fresh start.
Pretty much, yeah.
Okay, so those are the inherent challenges. Let's talk about some of the solutions that are coming out, some of the really innovative stuff. And one that I found really fascinating is Google's Titans architecture.
Yes.
And it's actually described as being inspired by human memory. So what's the main idea behind it?
Well, what's really interesting here is that Titans is actually designed to learn and memorize stuff dynamically during what we call the inference phase.
Okay.
So that, while the model is actually being used not just during its initial
It's
training.
learning as it goes.
Exactly. It's a big shift from how we traditionally think about models, where most of the learning happens beforehand. And Titans adapts its memory based on how much surprise or significance it sees in the data coming in.
Surprise. So it's not just passively processing information. It's actually making judgments about what's important enough to remember.
Exactly.
That's really interesting. So how does it actually do that? I mean, how does it determine what's surprising and what to keep in its memory?
Well, it uses what we call the gradient of the network's parameters
Okay.
with respect to the input. So think of it this way. If the incoming data causes a big change in the model's internal state, like a high gradient,
Yeah.
that means it's something unexpected,
Something new.
right? Something that doesn't fit its usual patterns.
It stands out.
Exactly. And the higher the gradient, the more likely it is that this information gets stored in long-term memory.
So it's not just storing everything. It's really picking and choosing based on what it finds novel.
Exactly. It's about prioritizing the information that's most likely to be important because it's different.
It's like a filter.
Yeah, you could say that.
That's really cool. Now, I understand there's also this adaptive forgetting mechanism, so it's not just holding on to everything forever.
Right, because if it kept everything, eventually the memory would get overloaded.
It'll get full.
Yeah, exactly. So Titans also has a way to discard information that's no longer useful so that it can focus on what's new and important.
It keeps things fresh.
Exactly.
That's a big difference from standard transformers, right, which don't really have that active pruning process.
Right, they're more static in how they handle memory.
Okay, so now Titans has these different ways of actually using its long-term memory, right? There's memory as context, or MNA, memory as gating, or MAG, and memory as a layer, which is MAL.
Yeah.
So can you quickly walk us through how these different approaches work?
Yeah, so MAC basically combines the data from long-term memory with the current input, so it gets a more complete picture.
Yeah.
This seems to be particularly useful for very long sequences
Makes sense.
and tasks that are kind of similar to retrieval augmented generation, or RAG, where accessing information from way back in the sequence is really important.
Right.
Now, MAG uses dynamic gating mechanisms to control how information flows between short-term and long-term memory, allowing the model to kind of switch its focus depending on what's needed for the task.
You can prioritize.
Exactly. And then MAL treats long-term memory as a separate processing layer.
Okay.
So historical context gets deeply integrated into the information processing.
It becomes part of the process.
Right.
Wow. Okay, so that gives us a much clearer picture of how Titans utilizes that long-term memory. Now let's shift gears a bit and talk about another really significant advancement, and that's Mamba.
Okay.
This one takes a totally different approach based on these structured state space sequence models, or S4.
Right.
So what's the core concept here, and how is it different from that transformer model we were talking about?
Well, Mamba is really a departure from the transformer approach.
It's doing its own thing.
Yeah. Instead of using attention mechanisms, it uses these S4 models, which are designed to efficiently model long-range dependencies in sequences.
Yep.
Mamba's innovation is in its selection mechanism,
Okay.
which allows the parameters of the S4 model to adapt based on the specific input.
So it's tailoring itself.
Exactly. It can filter out less relevant information and focus on what's really important.
It's selective.
Right. And the key to this is that the B and C matrices within the model are what we call time varying,
Time area.
meaning their values change depending on the specific input token being processed, so it allows for very precise filtering.
It's very dynamic.
It is.
So unlike attention, which looks at all the words in a sequence,
Right.
Mamba is more focused on how the current input changes its internal state and processing.
Exactly. And that leads to some pretty big advantages.
Like what?
Well, for one, it means Mamba achieves what we call linear time complexity with respect to the sequence length. So as the sequence gets longer, the computation time increases at a much slower rate than with transformers, which are quadratic.
So that's a big deal for processing really long sequences.
Huge. It opens up possibilities for working with massive amounts of data.
Wow, okay. And what about its architecture?
Mamba also has a much simpler architecture than transformers.
Okay.
It uses a single SSM block instead of all those complex attention and MLP layers.
So that means it's faster.
Yes, inference times are significantly faster.
And I read the Mamba is also hardware aware.
It is. It's designed to be very efficient on GPUs.
Oh, okay.
So it utilizes techniques like kernel fusion, which combines multiple operations into one, making computations much faster.
It's streamlined.
It is, and it also has optimized memory usage.
Okay, so it's really taking advantage of what modern hardware can do.
It
All right, so we've covered the basics of transformers, the innovative approach of Titans, and the efficiency of Mamba. Let's compare them a little bit more directly. Starting with how they each manage memory. So how does Titans stack up against the more traditional transformer in that respect?
Well, the key difference is that transformers rely mainly on that short-term context window through the attention mechanism.
Okay.
They don't have a dedicated long-term memory component like Titans does.
So Titans has that extra storage.
It does, and that allows it to retain information from much earlier in the sequence and to manage its memory dynamically through forgetting and learning, which standard transformers can't do.
Okay, and when it comes to efficiency and handling those really long sequences, it sounds like Titans might have a big advantage.
It does. Transformers struggle with long sequences because the computational cost goes up so quickly.
Right, yeah.
But Titans is designed to handle much longer sequences.
Like, how long are we talking?
Potentially millions of token.
Mil-
Yeah, it uses a more efficient memory system that can compress and store information without reprocessing everything, which makes it much faster.
And its training process is also optimized for speed.
It is.
Okay, what about handling those long-range dependencies? Where things that are far apart in the text are actually connected in meaning. Transformers can theoretically handle that, but does the effectiveness drop off with distance?
It can, yeah. While attention can capture those long-range dependencies in theory, as the distance between related elements increases, it becomes harder for the model to make those connections.
Because there's so much in between.
Exactly. And the signal can get lost, and of course, it's computationally more expensive to do that.
So it's a trade-off.
It is, but Titans tackles this head-on with its long-term memory,
Okay.
which is specifically designed to learn and remember that historical context.
So it can make those connections even over long distances.
Right, it uses both short-term and long-term memory during inference, and it's guided by that surprise metric we talked about.
So it's smarter about what it remembers.
You could say that.
Okay, and one more thing on Titans and Transformers. How do they approach processing the input sequence itself?
Well, transformers tend to treat all parts of the input sequence kind of equally. They don't really prioritize remembering surprising information.
It's all the same to them.
Pretty much, yeah. But Titans is designed to remember those surprising or unexpected events better,
Okay.
which allows it to use its memory resources more efficiently.
It's focusing on the important stuff.
Exactly.
Okay, so now let's compare Titans to Mamba, which takes a very different approach.
Right.
So what are the key differences in how they handle that long context and those dependencies?
Well, the biggest difference is in their core strategies.
Okay.
Titans uses a kind of hybrid approach.
Okay.
It still uses something like the transformer for short-term processing, but it adds that explicit long-term memory and dynamic learning.
Okay.
Mamba, on the other hand, is a more radical change.
It's going all in.
It's using these selective SSMs as a possible replacement for attention altogether and focusing on efficiency and linear scaling.
So it's a fundamentally different architecture.
It is.
Okay. And architecturally, how do they compare?
Well, Titan seems to build on the transformer even though the underlying model doesn't change during inference.
Okay.
Mamba is a much bigger departure from that, using SSMs as its basic building blocks.
So Titans is more of an evolution and Mamba is a revolution.
That's a good way to put it.
And what about their performance? What have we seen in the research?
Both have shown really impressive results.
Okay.
Titans is doing well in language modeling, common sense reasoning, even in fields like genomics.
Wow, a wide range.
It's often outperforming standard transformers and recurrent networks, especially in those long context tasks like needle in a haystack and Babylon, and in some cases it's even beating models like GPT-4 and Llama 3.
Really?
Yeah, Mamba is also achieving state-of-the-art results across different areas. It's particularly good at things like selective copying and induction heads, and it scales much better than those attention-free models.
So they both have their strengths.
They do. Now, some sources suggest Titans might outperform Mamba 2 on some benchmarks, but direct comparisons are still ongoing. And the best choice really depends on the specific application.
It's still early days,
It is.
but it's clear that there's a lot of exciting work happening beyond just scaling up transformers.
Definitely.
And it's not just Titans and Mamba. There are other interesting developments in LLM memory architectures.
There are.
So what else is out there?
Well, we're seeing a trend towards hybrid architectures that combine different approaches.
Okay.
A great example is AI 21 Labs Jamba.
Good.
This model combines Mamba's SSMs with transformer components and even uses a mixture of experts architecture.
So it's like a best of both worlds.
Exactly. The goal is to get better memory footprint and throughput and handle really long context, like up to 256,000 tokens.
Wow, that's a huge context window.
It is.
Okay, so it's taking the best parts of each approach and putting them together.
Right.
And what other advancements are we seeing?
There's also a lot of work on memory augmentation techniques.
Oh,
So these are ways to improve the memory of existing LLMs without retraining the whole model.
so you're adding to what's already there.
Exactly. A good example is IBM Research's Camelot, which stands for Consolidated Associative Memory Enhanced Long Transformer.
Okay.
This one basically adds an associative memory module to a pre-trained LLM,
Okay.
so it can handle much longer context windows without needing to retrain everything.
That's really clever.
It is. And then there's MEMLLM, which adds an explicit structured memory component.
So it's like giving the LLM its own database.
You could think of it that way. It's especially helpful for knowledge-intensive tasks and can reduce hallucinations.
Okay.
And there are frameworks like Unimem and the Memorizing Transformer that are exploring ways to integrate external memory into the transformer architecture itself.
So it's not just about changing the architecture, it's about adding external memory too.
Right, both approaches are important.
Okay. And are there any like completely new architectures that are worth mentioning?
Yeah, there's one called the Obsidian Memory Transformer.
Okay.
It's inspired by Titans and has its own long-term memory mechanism for handling large context windows.
Okay.
It's implemented in optimized C++ and CUDA, so it uses less memory and trains faster.
So it's more efficient.
It is.
Wow. It seems like researchers are tackling this memory problem from every angle.
They are.
And it's not just the software and architecture, right?
No.
Hardware is also playing a huge role in making all of this possible.
Absolutely. Hardware advancements are crucial for supporting these memory-intensive AI tasks.
What are some of the key hardware innovations that are happening right now?
Well, one exciting area is processing and memory architectures, or PM.
Okay.
These architectures integrate computing units directly into the memory chips.
So the processing happens right there in the memory.
Exactly. This could really reduce the bottlenecks caused by moving data between the processor and memory.
It streamlines the whole process.
Yeah, it leads to much better performance and power efficiency, especially for LLM inference. And one example is PMAI,
Okay.
which is designed to work with existing DDR5 and LPDDR5 memory without major modifications.
So it's compatible with current technology.
It is.
That's great. Okay, so we've seen innovation at the architectural level, in augmentation techniques, and even at the hardware level. It really emphasizes how important memory is for advancing AI.
It really does.
Now, let's step back for a minute and revisit the basic idea of memory in LLMs.
Okay.
We touched on this earlier, but can you clearly explain the difference between parametric memory and working memory?
Sure. So parametric memory is all the knowledge that an LLM learns during training and stores in its weights and biases.
Like it's long-term knowledge.
Exactly. It's like all the facts and relationships it knows and how it understands the world, and this allows it to retrieve information, make connections, and reason logically, but it's only as good as the data it was trained on.
So garbage in, garbage out.
Basically, and working memory is more like our short-term memory.
Okay.
It's what the LLM is focusing on right now, and in LLMs, this is represented by the context window,
Right.
which lets it consider the current input and what came before it to stay on track.
Keep it all coherent.
Right. And one way to try and extend this working memory is by just adding the whole conversation history to the context.
Okay.
But this runs into the limits of the fixed context window size.
It can only hold so much.
Exactly.
Okay, so parametric memory is the deep knowledge, and working memory is the immediate focus.
That's a good way to think about it.
Now, we've already talked about some architectural changes like sparse attention and windowed attention that can make memory more efficient.
Right.
What are some other techniques being used to boost the memory capabilities of LLMs?
Well, besides those, there are these long-range transformer architectures that are being developed. They're designed to get around the limitations of that context window.
They handle longer sequences.
Exactly. And we've also talked about retrieval augmented generation, or ARA,
Right.
where you combine the LLM with external knowledge bases, often vector databases,
Okay.
so the model can pull in relevant information before it generates a response.
So it's not limited to what it already knows.
Right, it gives it access to a much wider range of knowledge and keeps its answers grounded in facts.
Which helps with those hallucinations.
It does, and semantic search is really important for making that retrieval process work well.
Okay.
And then there are these hybrid strategies that combine things like windowed buffers for recent interactions with summarization for older parts.
So you're getting the best of both worlds.
Exactly.
Okay, WAREG really seems like a powerful way to overcome those limitations of the model's internal knowledge. Um, Now, let's shift our focus a bit beyond LLMs to intelligent AI agents.
Okay.
For these agents, memory is arguably even more important because they're not just generating text. They're perceiving, reasoning, and acting in the world.
Right. It's crucial for them to learn and adapt.
Exactly.
Right.
So how does memory work in these intelligent agents?
Well, for AI agents, memory is not just about recalling information.
It's more than that.
Yeah, it's essential for them to learn from experience, adapt to new situations, and make smart decisions based on what they've encountered before.
It's how they make sense of the world.
Exactly. They need to remember past states of their environment, understand the consequences of their actions, and build a coherent understanding of how things work.
So it's really about learning and adapting.
It is.
And just like with human memory and LLMs, there are different types of memory for AI agents, right?
Right.
We have short-term memory, which is about the immediate context. How is that typically implemented in an agent's architecture?
Well, in AI agents, short-term memory is like a temporary buffer. It
Yeah.
holds recent sensory input and the current context of what the agent is doing.
Okay.
It usually lasts for a short time, from seconds to minutes, and has a limited capacity.
So it's not meant for long-term storage.
No, and it's super important for things like conversational AI,
Mhm.
where the agent needs to remember the previous turns in the conversation to respond properly.
To keep the conversation flowing.
Exactly. And in more dynamic situations, like with self-driving cars, it's used to process all that real-time sensory data.
Okay.
It's often implemented as a simple buffer that keeps track of recent events or observations.
So it's constantly updating.
Right.
And then we have long-term memory, which is about accumulating knowledge and learning over longer periods.
Right.
What are the different types of long-term memory that we see in AI agents?
Well, long-term memory in AI agents is about storing information for much longer periods,
Okay.
with a much larger capacity than short-term memory.
So it's like the main knowledge base.
You could say that, and it's usually divided into a few main types.
Okay.
We have episodic memory, which is about remembering specific past events or experiences.
Okay.
This is important for case-based reasoning, learning from past situations.
Right.
Then there's semantic memory, which is about storing general knowledge like facts, definitions, rules, and domain-specific information.
So it's the general knowledge about the world.
Exactly. And then there's procedural memory, which is about remembering learned skills and behaviors.
So it's how the agent actually does things.
Exactly. And these different types of memory can be implemented in a lot of ways, like logging events, using knowledge bases, vector embeddings, and even RGAG.
So there's a lot of flexibility in how it's done.
There is.
Okay. So can you give us some examples of how these different types of memory might be used in a real-world AI agent?
Sure. So let's say you have an AI financial advisor.
Okay.
If it remembers a client's past investment choices, that would be episodic memory.
Okay.
If it knows the definition of a specific financial term, that's semantic memory.
Right.
And if it can automatically execute a trade based on learned procedures, that's procedural memory.
Just about remembering events, knowing facts, and having skills.
Exactly.
Okay, now building AI agents with all these different memory capabilities can be really complex.
It can be.
Are there any frameworks that have been developed to help with this?
Yes, there are several frameworks that are becoming more and more sophisticated.
Okay.
One example is LangChain.
Okay.
It's specifically for building memory-enabled agents.
Okay.
It provides tools for integrating different memory components with APIs and reasoning workflows.
So it's a toolkit for building agents with memory.
Exactly, and it connects to lots of different memory backends like vector databases.
So it's very flexible.
It is, and then there's LangGraph, which builds on LangChain.
Yeah.
It uses a graph-based architecture for more complex multi-agent systems.
Okay.
And it supports hierarchical memory graphs, which are great for tracking dependencies and enabling better learning across multiple agents.
So it's for more complex systems.
Right. And then there's Crew AI.
Okay.
This one focuses on role-based agents and has a structured memory architecture with built-in support for different memory types.
Like what kind of types?
Well, it has short-term memory, often using RAG, long-term memory using SQLite 3, entity memory also with a RAG, and contextual and user memory.
So it has everything covered.
Pretty much, yeah. And it uses agentic RAG, which is a new approach to retrieval augmentation.
Okay.
And finally, there's autogen.
Okay.
It mainly uses message lists for short-term context in agent conversations.
Okay.
But it has good integrations with external storage for long-term memory.
So it's focused on conversations, but can still handle long-term stuff.
Exactly.
These frameworks sound really helpful for developers who are building agents with sophisticated memory capabilities.
They are. They make the process a lot easier.
Okay, so now let's dive into the actual hardware that's behind all of this.
Okay.
We're talking about the current memory technologies and the recent advances that have happened.
Right.
So let's start with volatile memory, like RAM.
No.
We're currently transitioning from DDR4 to DDR5 as the main system memory. What are the key improvements in DDR5 that are especially important for AI?
Well, DDR5 has brought a lot of improvements over DDR4.
Like what?
Well, the speed, bandwidth, and capacity have all gotten much better.
Yes.
We're seeing data transfer rates of over 6,400 megatransfers per second. Wow.
Which means data can move around much faster, and that reduces those memory bottlenecks that can slow down AI.
So it's all about speed.
Yeah, pretty much. And DDR5 is also more energy efficient and has lower latency.
Okay.
And the capacity per memory module has increased too, which is important for those large AI models and data sets.
Right, they need a lot of space.
They do. And tests have shown that just using faster DDR5 memory can actually make LLM inference noticeably faster.
So that's a simple but effective upgrade.
It is.
Okay, now for GPUs, which are essential for both AI training and inference, we have high bandwidth memory, or HBM, and the latest version is HBM3E.
Right.
So what kind of performance jumps are we seeing with HBM3E?
HBM3E is a big step forward for GPU memory.
Okay.
We're talking bandwidth over 1.2 terabytes per second.
Terabytes per second.
Yes. And
Yeah.
capacity is up to 24 gigabytes per 8 high cube.
That's a lot.
It is. This means much faster training for large models and better inference performance, especially for those massive models with billions of parameters.
And major memory manufacturers are already shipping HBM3E solutions.
So it's available now.
It is. It's being used in the newest high-performance AI platforms.
That's exciting. And are there plans for future versions?
Yes, HBM4 is already in development.
So it's going to get even faster.
It is.
That's incredible. Now, what about the more traditional graphics memory, GDDR?
Okay.
We're on GDDR6 right now. Does it still have a role to play in AI with all these advancements in HBM?
Absolutely. GDDR6 is still very relevant.
Okay.
While HBM is the top choice for those really intensive tasks, GDDR6 offers a great balance of bandwidth, cost, and availability.
So it's a good all-around option.
Yeah, and it's especially useful for AI inference, particularly at the edge, and for applications where cost is a big factor.
Okay.
We're seeing GDDR6 with bandwidth up to 96 gigabytes per second per device,
Okay.
and capacities up to 48 gigabytes in some high-end GPUs.
So it's still very capable.
It is.
So it's a workhorse for inference, while HBM is the powerhouse for training.
That's a good way to think about it.
Now, what about for mobile and embedded devices where power consumption is a big concern?
Yeah.
We use low power, double data rate memory, or LPDDR in those devices. What are the recent developments in LPDDR that are relevant for AI?
LPDDR is essential for on-device AI in those battery-powered devices.
Okay.
The newest standards like LPDDR5 and its variants, LPDDR5X and LPDDR5T, are designed for high bandwidth and capacity with low power.
So they're perfect for mobile.
They are. LPDDR5X, for example, can reach data rates up to 8.533 gigabits per second,
Okay.
and capacities up to 64 gigabytes.
So that's enough to run some decent-sized models.
Yeah, you can even run models like Llama 2 on mobile with LPDDR5X, and the new LPDDR5T pushes that even further with speeds up to 9.6 gigabits per second.
That's impressive.
It is. These advancements are making it possible to do more and more AI tasks right on the device itself.
Which is great for responsiveness and privacy.
Exactly.